Sir, I was actually wondering regarding the selective repeat protocol, sir. Like, why do we
Yeah.
really need the negative acknowledgement? Like, let's say if the receiver side doesn't send any acknowledgement, then there will be automatic timeout on the sender side, and it will retransmit the packet.
Yes, so negative acknowledgement is one of the options. Whether it will be actually implemented in a real protocol, that's a different question. So that was a theoretical model of what can be done in a transport layer. Okay, it doesn't necessarily mean that it will be implemented in every transport layer protocol. So TCP that we are studying now, it doesn't really use any explicit negative acknowledgement, but through the ordinary acknowledgements only, it gives an idea of whether a packet has been uh, either whether up to how much has been received, and uh, what else is missing, and from that the user can get an idea. So TCP is basically a sliding window, as you will see. Okay. Let us just progress along the class, and then you will get the idea. Okay.
Sure, sir.
Just be a little patient. Okay. So we have to be a little fast now. Okay. The problem is that we are severely short of time. Okay. Next week is your spring break, so there will be no class. And just I want to inform you that although IIT has declared tomorrow to be a holiday, I mean, no classes will be held. Classes suspended tomorrow because of convocation. Because of the scarcity of time, I will take a class at the scheduled hours, that is from 8. I will try to finish as early as possible before 10, but I mean, if needed, I will continue till 10. Because I really want to finish TCP by tomorrow. Okay. Next week, I mean, first week of March, there will be no theory class. So it will be very difficult to finish the syllabus. Okay. Not even finish. I mean, just even to some satisfaction, some a little bit of satisfaction of the teacher also, it will be difficult to reach. Okay. Every week, it looks like we are missing the Tuesday classes. Okay. That is not acceptable. Anyways, the first stuff that we are going to discuss is in TCP, other than the headers, in the header, we have not discussed many of the flags. We will discuss this. But one of the things is how much is the data. Please note that the data in a TCP segment is optional, which is quite peculiar if you think about it, that the main idea of entire idea of a TCP segment is to transfer data from a sender to a receiver. But actually in the TCP segment, data is optional, because sometimes the TCP segment is also used just to check whether the receiver is still alive or not, and just to poke the receiver so that it comes back with some uh, I got disconnected. Can you hear me now again?
Yes,
Yes, sir,
sir.
you audible.
Okay, fine. I received a message that there was some network connection. Now the question is, how much is this data? Okay, calculation of what is the maximum amount of data possible in a TCP segment. This is a very critical calculation. In actual TCP, as we have discussed, there is a severe limit on how much data can actually be in practice actually being transported by a single TCP segment. So okay, so how do I calculate? The calculation is based on the fact that the I'm repeatedly getting a poor network message. Can you hear me, students?
Yes, sir, we can hear
Yes,
you.
sir.
I'm repeatedly getting a poor network connectivity message. Anyways, the calculation is based on the maximum size allowed in an IP datagram. Remember that an IP datagram encapsulates the entire TCP segment inside it and then adds an IP header and sends it. Okay, so every layer as you go down the network stack, it will encapsulate whatever it received from the previous layer, add its own header on it, and will continue. Now, the IP datagram segment has the payload size, which is the maximum, the size of the all the stuff that is other than the header is called the payload for an IP datagram. IP header itself is also 20 bytes. Now the IP datagram payload maximum size, there is a limit. It is the entire datagram size is 65535 bytes. 20 bytes is the header. So if you subtract, you are left with 65515 bytes. So the theoretical maximum amount of data is basically 65515 minus this 20 TCP header, or you can also do it 65535 minus 20 minus 20, whatever way you want to do it. So which is 65,495 bytes. Okay. This is if there is no option field. If there are option fields, then you have to keep on subtracting whatever amount of space is taken up by options. Anyways, so this looks to be a
Sir, you are not audible.
unfortunately, if you use such large segments, there, I mean, fragmentation might happen. Okay, I mean, IP might need to IP layer, there might be need to fragment it, because in the physical layers, even in the data link layer, there are severe limits on what can be the maximum size of the data field. For example, if you are looking at something like 802.11 Ethernet, Ethernet has a limit of 1500 bytes for the data. Okay. So
Sir, your voice is breaking up.
the IP header, you are left with 1460 bytes, which can be held in one Ethernet frame. So from 65,064 close to 64 kilobytes, we find that in practice, it can be as low as close to about 1.5 kilobyte. Actually, 1 kilobyte size frames are quite common in TCP. However, modern TCP, they perform first initially when initializing the connection, they actually go along the path when you are doing the handshake to figure out what is the maximum size of the data unit supported, because this 1500 byte is also not a, might be a different, it might be different along your network. This is for Ethernet. Okay, it might be different if they are using some other protocol at the data link layer. So it figures out what is the maximum segment size possible. It is called MSS, or maximum segment size, and that is determined by the maximum transmission unit, or MTU, of the link. Okay, and then that can be set as one of the options which have not been shown here in the packet, to tell the other side that, look, don't use any segment larger than this, because this link would not be able to deliver this, and there will be fragmentation in IP level. Fine. So this way of figuring out the maximum MTU length supported is called path MTU discovery. Okay, it uses something called ICMP protocol, which you will study probably when you study the network layer, and it can set up the MSS parameter. Okay. Now, how does TCP handle it? It can perform segmentation by checking the sender window after receiving an acknowledgement. In the acknowledgement, if MSS has been mentioned, if the window size is less than the MSS, then you can construct a single segment and left and send. Otherwise, it will construct multiple segments, each equal to the MSS and send. Okay, so these challenges we have already discussed. Window size 0 means there is no space left in the receive buffer. We had discussed connection establishment. Now we will come to connection release. How does connection release happen? It again uses a flag called FIN. Okay, FIN is one of the flags. If you look at this, FIN and ACK are one of the two different flags among all these flags. Among these 8 flags shown here, we will discuss 6 of them. Okay, SYN we have already seen. SYN and ACK we have already seen. Now we will discuss the working of FIN and ACK together when a connection is being stripped down. When a connection is being stripped down, site requests the connection to finish by setting the FIN flag. When that happens, this is called an active close action. Okay, so it is actively wanting to close the connection. Okay, so the server actually receives the FIN flag, and then the server understands that the other side, the client, wants to finish the connection or release the connection. In that scenario, it performs it goes to a closed state, which is called a passive closed state. Just a minute. When the server is also okay with the finish request, it performs a passive close in a sense that it refuses, once it goes to the passive close state, it refuses to read any more data anymore. Even if any more incoming data comes, it might refuse to accept it. Okay. Now it acknowledges the FIN request by setting the sending 2 segments, one with an ACK m+1 followed by a FIN n. N is its own sequence number. That thing, or the numbers that has been shown, m+1, these are basically the m is the sequence number of the client. Acknowledging m+1 means, which is the usual thing, the next expected sequence number from the client, and FIN n is the sequence number of the server. So it can send a FIN segment, and it also says that okay, I am done. Now the problem is, sorry, I shouldn't say the problem. One of the features is that the second and the third segments, the ACK m+1 and the FIN segment, they can actually be combined into one segment and sent by the server. There is no problem. Finally, when this is received, the client acknowledges by sending n+1, ACK n+1 to the server. Now, along with these FIN messages and the ACK messages, please understand that as we have seen, because of this 3-army problem, there is no solution to this is graceful termination of a connection. Okay, everything worked perfectly and connection was terminated perfectly. This unfortunately does not There is no theoretical guarantee that this will happen. Okay, as we have discussed in length earlier. Now, as usual, the client and the server, then it starts their own timers to unilaterally close the connections after they have understood that the other side wants to terminate the connection. Okay. So what I mean by that is that after this fin is sent from the client, it will start a timer, and even if ACK_m+1 and fin n does not reach it beyond a certain point, it will close the connection unilaterally. Similarly, once the server gets a fin request, fin packet, it will send the ACK and fin, and then it will start a timer and it will also unilaterally close the connection without bothering whether ACK_n+1 will finally, if it reaches, very good, but if it doesn't, it will close. There are separate TCP timers dedicated for this connection release mechanism, as we will see. So there are some bombastic state diagrams. Again, these are nice state diagrams. You don't need to memorize them or anything, but these are very nice state diagrams which basically show you the connection establishment and the connection closure. The dashed lines represent the server actions and the solid lines represent the client actions. As usual, the way these milli machines are shown in state diagram, there is an input. After that, there is a slash and an output or an action. Okay. So these are milli machine state diagrams for which all these inputs and actions have been shown. So those of you already who have studied milli machines and Moore machines are definitely students of electrical sciences. They should be familiar with this concept. And other department students also, those who are not from electrical sciences, probably you have also studied this. If not, it's not but actually essential to understand what is the difference between milli machine and Moore machines, but these are milli machine state diagrams basically. Fine. Then TCP sliding window, we have already seen that window size is acknowledged, is advertised by the receiver, and the sender respects that. Later on, we will see that the sender also maintains its own concept of a window size. The window size of a sender is not its buffer, it is something else. Sender side also has a buffer, but that is not its window. Okay, sender side window in TCP is something else. We will see. It's slightly complicated concept. Okay, first of all, we discussed this diagram earlier, but because this is a very important diagram in the context of understanding TCP, we will study it again. This has a parameter called a window size, which is there in any TCP segment. Acknowledgements are cumulative. So if say initially the receiver buffer is completely empty and the sender somehow had earlier received information from the receiver. So this is like already three-way handshake, etc. has already happened. So the sender has an idea how much space is left at receiver. Maybe the receiver told the sender that 4 kilobyte is available. You can say window size is 4 kilobyte now at receiver. So sender application does a 2 kilobyte write, because 2 kilobyte is less than 4 kilobyte. Immediately that is sent out by the sender as the first segment. This sequence number is 0. Okay, remember it is byte numbered. Okay, so whatever data is contained in this segment has a sequence number starting from 0 byte to 2047 bytes. Okay, that is the range of numbers of these bytes. When it reaches the receiver, this is accepted, and then the receiver has 2 kilobytes sent. The receiver sends back an acknowledgement saying that my next expected byte number segment should start at byte number 2048 and available window space is 2048 bytes. When the sender gets that, again, if an application does a 2 kilobyte write, immediately that can be sent out. But now the sender is blocked because it needs to hear back from the receiver that space is available if it's buffer. Otherwise, the sender will not unnecessarily disturb the receiver by pushing more data. Okay, so this is one very, very important lesson. Repeatedly, we will see that. I mean, this is how we had studied earlier also in the topic, that there is an active coordination between the sender and the receiver about how much data can be pushed on the network. Okay. So TCP tries to behave, the TCP sender tries to behave properly and tries not to overwhelm the receiver by unnecessarily sending too much data. Now, finally, when this 2048 new segment reaches the receiver's buffer, its buffer is full. Even the first 2 kilobyte segment, which is now, this is a FIFO structure. Okay. So when the first 2 kilobyte segment, which is now occupying the right half of the buffer, even this has not been received till now. Okay, by the application. So it waits, but it does send an acknowledgement saying that I have received successfully till byte number 4095. My next expected byte number is 4096, but my available window size is 0. When the available window size is 0, sender is blocked. Sender says, oh, I have no space left. Finally, the window receiver's buffer, from that, the receiving application removes 2 kilobyte. Okay. Immediately, the receiver sends another acknowledgement with respect to the window change. So now acknowledgements are also sent to indicate that the window size is changing. Very soon we will see a negative impact of this. Okay. I mean, this is good. Otherwise, the sender window, sending application would not move forward. But this also creates a lot of overhead, as we will see very soon. Anyways, so now an acknowledgement is sent saying that the window size is available now is 2048. The left half of the buffer now moves to the right. 2 kilobyte, this shaded portion is now moved to the right, and the white portion on the left is free because this is a FIFO. Everything gets transferred, say, or removed from the right hand side. When it receives, when the sender receives this acknowledgement saying that, well, 2 kilobyte is more available, it can again send up to 2 kilobyte, but if its application does a 1 kilobyte write, it can send a 1 kilobyte segment. In that case, 1 kilobyte comes in. Okay, and in time due course, when this 2 kilobyte is removed, this will also entirely move forward and it will. So this is not really out of order. This is kind of in order things are going on. Okay. So this is a sliding window, but this is kind of in order. So there is no concept of negative acknowledgement or anything, so that something can just come in and sit there out of order. So this is kind of in order sliding window. Quite simple, actually. I mean, quite simple in a sense, a little bit rigid, but quite simple to understand. The only new thing to learn here is that acknowledgement segments can be sent back with acknowledgement numbers from the receiver in response to its available buffer size changing, or if there is free space available in the buffer, it can send an acknowledgement. Okay. Another thing I want to mention, students have asked this earlier in previous batches. Don't get confused by this notation of ACK equal to 4096, etc. here, and earlier ACK m+1. So this is acknowledging m+1 is fine, but this also has certain flags set. Okay, so there are these there are two meanings of this ACK and the sequence numbers. Okay, so all these flags are being set. That's why these are shown as acknowledge ACK and this, and then the window size is this. The sequence numbers is this. Okay. So you have to understand what is the meaning of this.
Sir,
Now, so our moral of story is acknowledgements are of two types. One is sent just to acknowledge that I have received packets till up to this safely, and this is my next expected packet. And the other type of acknowledgement is just to say that some space has been made available in my receive buffer. You can send more. Consider a very pathological situation, but it's a true situation. It can happen in practice. Okay, in real life computing scenario. Consider a telnet application, telnet or SSH type of application, where you are remotely logging into a different system from your home computer or your computer or in your hall. And suppose the computer is in the department over a telnet is like a mechanism to do a remote login on a system. It's quite old. It's not used all the time. Say SSH, or there are unencrypted versions of SSH called RSH, etc. Whatever, you are doing some remote login. Now suppose you are typing, okay, stuff on a keyboard, and you expect that terminal, that remote terminal that will show a command prompt that is on the server, that will also follow your keystroke typings. Your typing speed is very slow. In general, human typing speed is very slow. Okay, 40 words, 50 words at a time, or words at a time. Say so, like 200 characters in a minute is the speed of typing of extremely expert typists. So most of us do not type at that speed. So you are say typing at a speed of say 1 character per, or like 2 characters per second, 2 characters per second, something like this. So to your TCP sending entity on your system, so you type 1 character, which is say 1 ASCII character at a command prompt. It is a 1 byte thing. When it reaches the TCP entity, it creates a 21 byte TCP segment because it has a 20 byte header. You cannot do anything about the header. There will be a 20 byte header always with your 1 byte data. Okay, then it sends it to the receiver. The remote TCP entity on the receiver receives it, sends an acknowledgement. Okay. But that 1 byte will be then read by the application, maybe not immediately, so it cannot piggyback the window update on the acknowledgement. So it sends an acknowledgement 20 byte, then a window update, and again 20 or 21 byte, whatever. Okay. When the receiver application reads 1 byte, and then you need to see that segment, see that character displayed on your screen. So this is basically saying that the receiver side application should echo back the character to you to show that, to satisfy you that yes, it has typed properly on a remote terminal. So that is again another 21 byte TCP packet. So how many packets flowed? 4 packets in total flowed. One was the stuff you sent, and 3 packets was 1 acknowledgement, 1 and window update, and 1 echo for the echo mechanism. That's a huge wastage of bandwidth when the amount of data is small. This was just 1 byte of data. This is the limiting amount of data, smallest amount of data, okay, that you can send. And it's a massive wastage of bandwidth. Okay, how to solve this? Then the receiver TCP implements something called a delayed acknowledgement. In the delayed acknowledgement, the receiver side TCP entity says that, look, they are sending very small amount of data in each segment. Okay, so let me wait for some more time. I will not react immediately to everything that I am receiving. Okay, let them send some stuff more. Then I will acknowledge and give the window update at the total up to whatever I have received, and the cumulative TCP gets cumulative acknowledgement. We have already studied. Okay, so I will use that property to save on some bandwidth, and I will not immediately give a window update. I'll also possibly save bandwidth there, or maybe I will combine the acknowledgement and window update for several received segments. How much should I wait? Well, TCP chooses up to 500 millisecond. So within 500 millisecond, if new stuff is coming in, I will wait again till 500 millisecond probably, and then if nothing has come in within 500 millisecond interval, I will finally send a cumulative acknowledgement and cumulative window update. But I will wait till then. Very, very simple, easy to understand, and straightforward common sense scheme at the receiver. Okay, but the sender in the meantime in 500 milliseconds, maybe he can send multiple short data segments, maybe 2 more. So you will be combining the data for 3 short segments in one go at the receiver and send it back. Now, for the sending entity also, still sending out such small one, fine, the receiver tried its best to save some bandwidth, but what about the sender? The sender will say, well, I am sending out 1 byte data segments inside with 20 byte headers. This is humongous wastage. I would also be a little bit more prudent or wise about using bandwidth. So something called Nagel's algorithm is used. What is Nagel's algorithm? When the data comes into the sender in small pieces, it sends the first piece and it buffers all the rest until the first piece is acknowledged. Okay, so until the first piece is acknowledged, it will buffer. Then it sends out all the buffered data in one TCP segment and again starts buffering until the next segment is acknowledged. Okay, so what happens is only one short packet, the initial one that was sent out, that can be outstanding at any point of time. Otherwise, from the next segment onward, everything is of decent length. Okay, reasonable length. So that way it says that I am not sending out data packets, TCP segment, very short segment, multiple TCP short segment, only one TCP small segment I initially sent out. And once that is acknowledged, I will again send a large TCP segment. Then when it is acknowledged, I will again send the large TCP segment. I won't be that, what should I say, that impatient in immediately sending out stuff, whatever I am receiving in my buffer. I will just wait and buffer to build up large segments and send out. So in one way, we said that up to 1460 byte segments can be sent on TCP in most cases. Okay, so we were said that is very unfortunate because theoretically TCP could have sent out segments as large as over 65,000 bytes in one data bytes in one segment. That's why we said 1460 is very unfortunate. Here we are in a situation where the amount of data sent out is so small, like 1 byte, that this is at the other end of the spectrum. Now we are concerned that we are wasting too much bandwidth. We are just basically repeatedly sending headers with very small amount of data. So I am not liking that. I would try to amortize the header cost with lot of data. Okay, so let me buffer. 1460 bytes is lot of byte. I mean, if a human typist is typing 1,460 characters is huge. So I will buffer stuff, then I will send. Okay, I won't be that greedy, that impatient in immediately sending out stuff. But now think of delayed acknowledgement and Nagel's algorithm. Okay. Suppose they are implemented together. Now what happens? Now sender sends out to the first 1 byte or very small segment. Receiver receives it. Receivers looks at the segment and say, "Arey, only 1 byte of data has come. What's the point of immediately sending the acknowledgement and the window update? Let me wait for some time and get more data from that site." So that is like delayed acknowledgement. Nagel is, whereas on the other hand, the sender side, Nagel is saying, okay, I am not receiving any acknowledgement from the sender, so let me wait. That is how Nagel works. So this creates a starvation. Both of them are waiting on the other side. Finally, the sender will send after 500 millisecond, but 500 millisecond might be a wastage of time. Okay, every time it like spends 500 milliseconds and then send something. So that's a wastage of time actually. So together they do not always work properly. Okay. So this is called something called a silly window syndrome that can in turn happen when the receiver side application is receiving reading data very slowly. Okay. So Nagel's algorithm combined with delayed acknowledgement is a problem. And now we are studying another issue, which is the receiver's buffer is full. It is full of data. Okay, that it is waiting for the receiver side application to read. But the receiver side application reads only 1 byte at a time. So there is only 1 byte available. So window update is sent saying 1 byte is available. The sender says, okay, 1 byte is available. I will send a 1 byte segment. What can I do? Sends 1 byte. Again, buffer is full and it stops. So this is called a silly window syndrome. Only the window update segments of 1 byte, 2 byte, small amounts reach the sender, and sender sends out small sized data segment. Receiver is sent. Sender must respect the receiver size available window size. So now the receiving application is very slow, so the sender is suffering. So Clark noticed this, researcher called Clark, and he said, again, do not send window updates for 1 bytes. Wait until the sufficient space has been available at the receiver buffer. Again, a very simple-minded solution. That don't get so proactive and send an update for a 1 byte available space at the receiver buffer. Let the receiver buffer empty a little bit. Let it take time. Let the receiver application remove some more data. Then you send something. Okay. So, for example, some implementations might use that when the receiver buffer is at least half empty, that time you send a window update saying that okay, this much space is now available. So together there are two different problems and two different solutions. Nagel's algorithm and Clark's solution to the silly window syndrome, they are complementary to each other. Nagel's algorithm was trying to solve the problem caused by the sending application delivering this data to TCP very slowly, maybe 1 byte at a time. And Clark's solution was trying to solve the problem of the receiving application fetching the data from TCP very slowly. They are complementary to each other. Okay, so they are used in practice in all applications. Delayed acknowledgement is also used but delayed acknowledgement combined with Nagel's algorithm sometimes can affect the performance of TCP. Now there are exceptions. There are two flags. One is called a push flag or PSH flag, and the other is called a urgent flag. Let me describe them. If you look at the TCP segment, fin, sin, reset, push, ACK and urge. So till now we have covered a fin, sin and ACK. Let me cover RST, PSH and urgent. First PSH, push flag. If the push flag is set, the application is requesting the sending side TCP to not to buffer it at all, immediately to send it out. Just send out whatever you have received in one burst in your sending buffer, just send it out in a segment immediately. And when the receiver receives it, it is requested to the buffer that please don't wait to send it to the application. Okay. I mean, somehow you inform the application that immediately this has to be read and push it, make the application forcefully, force the application to read it immediately. However, the push pointer, the push flag based mechanism works in order. Okay, by in order, I mean that it is not that it comes to the back of the FIFO and suddenly it will jump forward. It is not like that. It just tells the receiver side to immediately deliver the stuff to the application, not to waste time. When its turn comes, it's not out of order. There is another flag called the urgent pointer, urgent flag URG, combined with a 16-bit pointer called the urgent pointer. This is quite interesting and complicated. One thing I should mention is that the urgent pointer is not used very commonly. Okay, but the mechanism exists. If the urgent pointer is set, first of all, it is immediately sent out by the sender. And only if the urgent pointer is set to logic 1, or that is 1 is present in this URG field, the receiver side reads this urgent pointer value. This urgent pointer value is an offset from the starting of the data part of where urgent data is to be found, which has to be delivered to the application immediately, even if needed out of order. Do you understand? Say, for example, urgent URG flag is set to 1. And some urgent pointer value here, it is set to, say, it's a large 16-bit thing, say it is set to 10. That means, first of all, the sender TCP will immediately send out the segment. The receiver, when it receives, it looks at the segment and sees the urgent flag is set. Only if the urgent flag is set, it goes and reads the urgent pointer. Otherwise, even if some urgent pointer value is set to some junk value, it doesn't care. No, okay, the TCP say receiver doesn't process this 16-bit field at all. However, because the urgent field is set, it reads the urgent pointer and finds that 10 is given here. Then it goes to the data field and then moves 10 bytes from the beginning, and whatever is sent there, starting from that, it tries to pass to the application immediately, leaving out the first 9 bytes. Okay, so it will now start from the 10 bytes and first, try to deliver those first out of order to the application. Okay, so this is very, very, what should I say, very peculiar, and it's quite aggressive, and well, this is not used that much. Why it is not used that much, I'm not very sure. Maybe there are some security vulnerabilities or something, but in practice, it's not used that much. Okay. Then there is a flag called RST or reset flag. A reset flag, if it is, if any entity, any TCP entities receives a pack, it receives a segment where the reset flag is set, it understands that the other side wants to terminate the connection. Okay. The other side has terminated the connection, then there is no point continuing this connection anymore. Maybe the other side has crashed, maybe the other side has got into some trouble with its TCP stack and it has lost its state. Something has happened, or simply the other side is not interested in continuing with the connection. An example application of this very interesting application from, I have not read it in any textbook, I've just read it online. I don't know whether it is true, but probably it is true. In China, several very common websites like Google, Facebook, etc. are banned. So from inside mainland China, you cannot you cannot access Google. Okay, which is very strange, but that's how it is. Now, the way, so there is a great firewall. Okay, China, it is said that the China has a great firewall around it. So the entire country is inside a internet firewall. So if an user say tries to reach www.google.com through his browser from inside China, the request is intercepted by the firewall. The firewall essentially what it does, it instead of forwarding the request further, it essentially sets the RST flag to 1 and sends back a segment to the sender entity, say sender side, and the sender side TCP immediately closes the connection. Because that's the meaning of RST, that it is not possible to set up the connection to whatever server you are trying to connect. So this is one interesting use of RST, can be used by firewalls also. I will not go into CWR and EC. These are important. I'm not denying these are important fields, but unfortunately we don't have that much of time. The EC is used for indication of congestions, etc. These have come into use relatively recently. Okay, so even 15 years back, these were not very common flags. But anyways, and there are still I think 4 bits unused. 4 flags are unused, which in future also this will come to get used. But CWR and EC, if you are interested in knowing about these flags, I would suggest please go and study, refer to the 5th edition of Tannenbaum, and you will come to know. In older editions of Tannenbaum, these flags are not even shown, because they had not become very common, or they had not become standardized at that time. So say 10, 12 years back. Okay, so these are quite recent developments. Now, the mechanism by which TCP handles out of order is not through a negative acknowledgement mechanism. It is slightly different. Okay. It can buffer out of order segments. Okay, but it doesn't send back negative acknowledgements. It still keeps on sending back cumulative acknowledgements. So it is not really not really exactly classical selective repeat, which we studied in the previous class. It is slightly different, but it has the ability to handle out of order packets. How does it handle? Well, suppose the receiver has received byte 0, 1, 2, then 3 it has not received, 4, 5, 6 and 7 it has received. Okay. Now under this situation, TCP has buffered them, but it has remembered that 3 has not yet come. So it cannot, it has made a promise to the application layer that it will deliver packets or bytes in order. So it cannot deliver this all of this 0, 1, 2, 4, 5, 6, 7, everything together to the application. If it had 3, then yes, all these 8 bytes it could have delivered to the application. Here it cannot do it. What it does is it sends a cumulative acknowledgement with acknowledgement number 3, acknowledging everything up to byte 2. Why acknowledgement number 3? Acknowledgement number 3 because it is saying that my next expected is 3. Again, it is saying my next expected is 3. Okay, even if it receives 4, 5, 6, 7, because it has not received 3, it will say that no, I have received till 2. You have to send me 3. Now, like 4 is received, again the duplicate ACK, that's what I said. The duplicate ACK with ACK number 3, next expected byte is sent. So try to understand this. So now duplicate acknowledgements are being sent because out of order bytes have reached the receiver. Okay, so when 2 was received, it sent an acknowledgement. Okay, that next expected is 3. 3 never reached it was sent by the sender probably, but it never reached the receiver. Instead 4 was received. Still when 4 was received, it sent back another acknowledgement saying, no, my next expected is 3. So it is very stubborn. It keeps on saying, I have not received 3. You send me 3. So in that case, the sender receives the duplicate acknowledgement. If it reads the duplicate acknowledgement, a congestion control mechanism is triggered, which basically slows down the sending rate. Anyways, because 3 has not been acknowledged, a timeout happens and the sender retransmits byte 3. After how much time would the sender retransmit? What should be the timeout interval? This depends on the congestion control scheme that is being enforced on receiving duplicate acknowledgement. And then after that timeout interval, sender will retransmit byte 3. How is that mechanism? What is the relationship between the congestion control mechanism and the timeout interval? We will study in detail. Okay, so just be patient. Now, suppose the sender retransmits byte 3. Once 3 is received, then the sender, then the receiver can send another cumulative acknowledgement with acknowledgement number 8, because now it has received everything till 7. Okay, so through not with negative acknowledgement, but through repeated sending of duplicate acknowledgements, it could understand or it could tell the sender that this thing was missing, please resend. Okay. Now, one question I wanted to ask is that why did timeout happen? How does the sender, fund basic question, how does the sender understand that byte 3 has timed out? Anybody, students? It has received many acknowledgements. In fact, it has received duplicate many acknowledgements for 2. But how does it understand that byte 3 is what has timed out?
It has not received ACK4.
Yes, it has not received ACK4 till now. ACK4 is corresponding to byte 3. Very good. So finally it retransmits byte 3. Everything, this fills up the blank in the receiver buffer. Everything up to 7 is available. Finally, it sends the cumulative acknowledgement of with acknowledgement number 8, which is the next expected byte. So let me stop here. Next, from tomorrow's class, in tomorrow's class, we will study something very, very interesting, which is the timer management. How does this timeout interval, etc. is controlled in TCP? Extremely interesting topic. OK, so thank you. And tomorrow we will have the class at 8 as usual. I'm now stopping the recording. Thank you.